P divides an plus 1, we have nothing to prove. See, what is our aim? Our aim is to show that P divides at least one of these factors. So if P already divides one of them, namely an plus 1, then we are done. So assume P does not divide an plus 1. We claim that this implies, this non-divisibility relation implies that actually P and an plus 1 are relatively prime. To prove this claim, we have to look at an exercise, and that is exercise 9. So we assume this result for now. When we prove exercise 9, it will be clear why this is the case. Okay, so this remains incomplete, but it will be completed. So for now we have got this, right? Okay, now you go back to the previous lemma. What did that lemma say? That lemma said that if A and B are relatively prime and A divides BC, then A must divide C. Now in place of A, you think of P, and in place of B, you think of an plus 1. In place of A, you have P. In place of B, you have an plus 1. And in place of C, you have this other product. Okay, A1, A2, up to an. So this is relatively prime to this, and this divides the product. So it has to divide the other thing. A1, A2, up to an. So by the previous lemma, I can write by the, you know what I am talking about, the other one, the previous one. By the previous lemma, P divides A1, A2, A3, etc. up to an. Okay, but what is the induction hypothesis? Assume that the result is true for some product of n integers, for any product of n integers. So this is the product of n integers, and this is the prime that divides their product. So it has to divide at least one of them, and that's what our induction hypothesis is, that assumption. But then by the induction hypothesis, P divides AI for some I lying between 1 and n. So in any case, you see that either P divides an plus 1, or if that's not the case, then P divides one of these. So in any case, P divides AI for some I lying between 1 and n plus 1. So this completes the induction. So this completes the induction and proves the corollary. This corollary is important, and it will be used in the proof of the fundamental theorem of arithmetic, which is the main result of this section. Okay, so now we will turn to the fundamental theorem of arithmetic, which says basically what we have discussed previously, that any positive integer greater than 1 can be factorized as a product of primes in an essentially unique way. So we are going to look at that now.